So in this video we are going to discuss about body area network architecture. Before going to that topic, we are going to discuss about a simple IoT architecture and wearable architecture. So first let us discuss about a simple and versatile IoT architecture. The interconnection of the things in IoT to a network that transport the data that will be eventually used by applications in the cloud or somewhere in between. In this video, our intention is not to promote any of the aforementioned architecture. It should be noted that IoT reference model may vary based on the industrial applications or the technology being deployed. An IoT reference model that highlights the primary building blocks common to the most IoT framework is presented, which is intended to help the listener in designing an IoT product. IoT reference model includes numerous elements such as sensors, actuators, protocols, and services. The framework presented here is a simplified IoT architecture that contains the most basic building blocks layers which can be used as a foundation to understand key design and deployment principles. These basic layers can be expanded on as needed based on the industrial specific use cases. If needed, the reader is referred to one of the more complex reference model covered in this video. So this is the simplified IoT architecture which consists of cloud, fog, edge and mist. Okay. So as we already know what is cloud, right? It is used for analytics purpose, controlling, archiving. Then fog is the next stage. Okay, so after analyzing the data, that is pre-processing, primary analytics, routing. Next one is aggregation, digitization, forwarding. The last one is sensing and actuating. So the first layer, perception and actuation. So this layer includes the sensing or perception systems where data is collected from the network environment, a process or a smart object performing a certain function to be used in decision making or analytics. An actuator can also be present at this layer that allows the smart object to perform an action, that is to switch on or off light, adjust an airflow of a valve, to increase or decrease an engine rotation speed and more. Some limited data processing, mist computing can occur at this layer if an immediate response is necessary. However, if more in-depth processing of data is needed, which requires more computational power and time, Then the data needed to be moved to the upper layer called fog and cloud data center. The second layer is data conditioning and linking. One can think of this layer to have two ends. One end which sit in close proximity to the sensors and actuators, which is responsible for aggregating the data and converting it into a digital system for further processing in the upper layer. On the other hand, which sit close to the layer 3, which contains the internet gateway, which receives the aggregated and digitized data and routes it over a wireless or wired network to the upper layer for further processing. The significance important of this stage lies in pre-processing the voluminous amount of analog information collected from the sensors in the previous stage and compressing it into the optical size for future analysis. Layer 3, which is network transport. Once the IoT data has been digitized and aggregated, it is traveled to the cloud or data center. However, the data may require further processing before this step is initiated. An infrastructure An infrastructure can be physically located close to the data source. It is easier and faster to act on the IoT network in or close to real time and provide an output. Thus, only the large piece of data that needed the computational and analytical power of the cloud would be forwarded. By minimizing the network utilization, security can be significantly enhanced, while improved response time and reduced bandwidth consumption could contribute to more efficient IoT systems. Multiple protocols have been created to optimize IoT data communication. Some networks are based on push model, whereas other networks rely on pull model. Other utilize hybrid approaches also. One very common protocol used in the IoT product is Message Queue Telemetry Transport (MQTT), which is a standard lightweight publish subscribe network protocol that transport message between devices. The network can be set up to be a publisher. The application can be set as the subscriber, and an immediate system is set up to act as a broker to relay the information between the publisher and the subscriber. Layer 4 is application layer. Non-time sensitive data that needs more in-depth processing gets forwarded to this layer to be analyzed, managed and securely archived. This layer is also used to control the smart object when necessary. Moreover, this layer instructs smart object to adapt to certain conditions based on deeper insight gained from historic analysis. The layer of simplified IoT reference model and their relevance to the cloud, fog and mist. These are the um, layers which is illustrated in the figure. Wearable device architecture. Uh, One could utilize one of the IoT architecture to design sophisticated wearable devices. However, due to the size constraint and limited computational power of wearables, a typical system architecture would include a gateway to the internet. That is example a smartphone with dedicated applications used for configuring the devices and for processing the perceived data. The gateway devices is also used for data visualization purpose where relevant process data are translated into a graphical representation. The perceived data are forwarded wirelessly using a low power transceiver, example BLE, Bluetooth Low Energy for basic processing. A thorough and insightful data processing take place in the cloud. So you can see the basic architecture for wearables. It consists of cloud, gateway, wearable devices, and user. Right. The cloud normally it will analyze for archiving and for management. Right. The gateway is configuring the basic analysis connectivity, and wearable devices is for perception control feedback. Right. The The processed data are then transferred back to the wearables for feedback, while a copy of it is archived at the data center. You can see obviously the gateway provides the mean of network connectivity for such back and forth communication. It should be noted that the wearables can either simpler or more complex than that it is shown in the figure. For instance, some wearable navigators used by the professional hikers connect directly to the GPS global positioning system. Thus, they bypass the gateway layer. But in some other uh, early fitness trackers relied they only on the smartphone for processing and feedback without the need to use the cloud service. So the conclusion is you can see the requirement of this IoT system are giving rise to a new architecture that address the emerging constraint and data management aspects of IoT. In order to address these needs, a number of IoT specific reference node models has been proposed. These features shared between these models are the interconnections of the IoT endpoint, the networks that connect them, and the application that manages them. Due to the unique requirement of IoT, centralized data management is no longer as practical as it is in traditional IT network. It is simply not practical to send data to the cloud over a backhaul connection for processing. Before it is sent to the cloud, data in the IoT systems are filtered, aggregated, and pre analyzed in layers close to the edge of the networks. So, these drives to a new concept called fog and mist computing. Now, let us discuss about body area network architecture. Many high-level architecture has been proposed for health monitoring systems that employ set of wearable sensors and their supporting communication and information storage networks. The most common system level functional architecture includes first one, networks of body sorry a network of sensor on the body that stores its data to a wearable or handheld data logger hub that then communicates wirelessly with the local base station or internet gateway. Second one, a central command center that receives data from these gateways. Third one, a network backbone infrastructure that facilitates the exchange of information between the command center and the appropriate medical service center. Example, external network. The BAN architecture often includes a connection to an external network such as local area network LAN, wide area network WAN, or the internet. This connection allows for remote access to the collected data, enabling healthcare professionals or authorized individuals to monitor the wearer's health status in real time or retrieve historical data. Fourth one, cloud or server infrastructure. The collected data from the band can be transmitted to cloud-based platform or dedicated servers for storage, analysis, and further processing. Cloud infrastructure provides scalability, accessibility, and computational power for advanced data analytics and machine learning algorithms. Fifth one, user interface and application. BAN architecture typically includes user interface and applications that allows the wearer or healthcare professional to interact with the systems. These interfaces may be smartphone applications, web-based dashboards, or dedicated software platforms designed to display real-time data, set alerts, and provide insights based on the collected information. Overall, the BAN architecture is designed to enable seamless and continuous monitoring of a person's health and well-being, offering benefits such as early detection of medical condition, personalized healthcare, and improved quality of life. At the body level, sensors communicate bidirectionally with wearable handheld data loggers, which then interact with the resources external to the wearer. Mesh sensor topology, wireless routing schemes, and other more complex topological approaches are typically unnecessary at the body level due to the close proximity of the wireless nodes. In addition, the peripheral technology that supports the local gateway and the extended backbone network infrastructure, which may include cellular systems, wireless local area network, and then home RF implementations, are mature, and treatment of such subsystems are addressed in numerous wireless texts. So if you see the diagram, a person is running, you can see a network of sensors. One is ECG and tilt sensor, then motion sensor. This data is given to a personal server through Zigbee, right? And further, it is transmitted using Bluetooth or WAN or GPRS via internet to the external environment, such as the data is given to a caregiver, medical server, emergency, weather forecast, physician, and it can be seen over a Fitbit type of devices. Okay. The conclusion is body area network BAM have body area network have significant implication in healthcare, wellness and various other domains. By providing continuous monitoring, personalized insights and real-time feedback, bands empower individuals to take control of their health, enable remote healthcare delivery and enhance the quality of life. As a As technology advanced and bands become more integrated and interconnected, they hold immense potential for revolutionizing healthcare and improving overall well being. Some of my reference for making these videos I have given below. First one, Analysa Bonfiglo and Dilo D. Rossi. Wearable monitoring systems, Springer 2011. Second one book is Gong Zong Yang Body Sensor Network, Springer 2006. Third one is Fundamentals of Internet of Things, IoT and Wearable Technology Design, IEEE Press, Willy Higher Road. Fourth one, Wearable Sensor Fundamentals, Implementations and Applications, edited by Edward Sassonovo, second edition. So thank you for listening to this video.